Day 244 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem. This time we're at day 244, and I don't see any signs of slowing down anytime soon, so let's get into it. Today we have question number 98, validate binary search tree. The difficulty level is medium, but you already know we're going to keep the solution as simple and easy to understand as possible, so let's get into it. Question says, given the root of a binary tree, determine if it is a valid binary search tree, BST. A valid BST is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key, and both the left and the right subtrees must also be binary search trees. So, let's break that down by looking at example one. Example one is pretty simple. In example one, we have the input root equals a binary search tree 2, 1, and 3. The output is true. We can tell that the output is true because this is a binary search tree, a valid binary search tree, because if we start from the root and go to the left child node, the left child node is less than the root, and if we go start from the root and go to the right child node, the right child node is greater than the root. So they satisfy both of all of these requirements, except for the third one. It's not really a subtree, but it satisfies these first two requirements because we go to the left, 1 is less than 2, and we go to the right, 3 is greater than 2, which makes it a binary search tree. So now let's look at example 2, where it's a little bit more tricky and the output would be false. And this one, we can actually go through all of the requirements because it has a binary search tree, or it has a subtree that we can actually go through and see if it matches that requirement, satisfies that requirement. So let's see. In example 2, we have the input root equals a binary search tree 514 null null 36, which is represented by this picture right here. The output is false. Explanation says the root node's value is 5, but its right child value is 4. So as we can see from the explanation, that this right here does not satisfy this requirement right here, the second requirement they give us. The right subtree of a node contains only nodes with keys greater than the node's key. So I guess the node's key is another word of saying the root. And in this case, 4 is on the right child. It's a right child node, right? So the right child node should be greater than the root. But in this case, it's less than the root, so we know that it's not a binary search tree, whereas everything else fits the requirements. So let's go through the other ones so you can see how it fits the other requirements, but this one is the only one that's wrong. So if we start from 5 as being the root and we go to the left child node, 1 is less than 5, right? So that satisfies this requirement right here. The left subtree of a node contains only nodes with keys less than the node's key. So 5 is the node's key. We go to the left subtree or the left child node. 1 is less than 5, so it satisfies that requirement. We know it doesn't satisfy the second requirement that says the right subtree of a node contains only nodes with keys greater than the node's key. It doesn't satisfy that because if the root is 5 and we go to the right child node or the right subtree, in this case, 4 is less than 5 when it should be greater than 5. They could have picked any number greater than 5 and it would have worked. But since 4 is less than 5, it's not going to work. However, if we looked at this subtree right here, this subtree is a binary search tree. If we just took out these two nodes, the root nodes and the left child node, the 5 and the 1, if we got rid of the 5 and the 1, this 3, 4, and 6 satisfies this third requirement of both the left and right subtrees must also be a binary search tree. This 4, 3, and 6 is an example of a binary search tree if this 5 and if it wasn't connected to this 5 and 1, because we go to the left of the 4, which is 3, and 3 is less than 4. We go to the right of the 4, which is 6, and 6 is greater than 4. So this right here, 3, 4, and 6 satisfy the binary search tree requirements of the right subtree. However, since 4 is less than 5, it gets messed up right there because this should be greater than 5. And everything on this right subtree should be greater than 5 as well. So now that we know what the question is asking, let's get into the fun part, the actual solution. But before we get into the solution, y'all, don't forget, if you need any new Apple AirPods, go ahead and check that link in the description. Then after you do that, don't forget to like, comment, and subscribe. Now let's get into it. Now, first thing we need to do for this solution, we need to figure out how we're going to traverse these binary search trees. And what we are going to do is we're going to use an in-order traversal, because the in-order traversal will let us see if one value to the left or the right is greater than the root node, right? Because with the in-order traversal, first we traverse the left subtree, then we traverse the root, and then we traverse the right subtree. So if we did an in-order traversal of this example 1 binary search tree, first we would traverse the left subtree, which would be 1. Then we would traverse the root, which would be 2. Then we would traverse the right subtree, which would be 3, right? And that lets us know, we can see just from the in order traversal that the numbers are in order, right? Or at least they're in ascending order. They might be different values for different binary search trees, but we at least know that the left subtree is smaller than the root and the right subtree is greater than the root by doing this in order traversal, right? So that's how we are going to traverse through this binary search tree using in order traversal. Now, the first thing we need to do to start our in order traversal is we need to create a variable that's going to keep track of the previous node value while we're doing our in order traversal. So in order to do that, we just come outside of this function inside the class, and we could just say private var prev colon, and that's going to be an integer. And once again, that's going to keep track of the previous node's value while we're doing our traversal. Now, we need to create our helper function, right? And this helper function is going to be what performs the in order traversal and validates the BST for us. So in order to do that, we're going to say private func in order, we just call it in order, open up the parentheses, underscore root, colon, and it's going to have a tree node, question mark, come outside the parentheses, and it's going to return a bool for us. Boom. Now we need a base case to check if the current node is nil and if it's valid. So in order to see if we need to see if the current node is nil or if it has a value, right? So in order to do that, we could just say guard let root equal root, else we could just return true, just like so. Now we need to come underneath that, and we need to recursively check the left subtree, and if it is not valid, then we need to return false. So in order to do that, we could just say guard, or excuse me, it doesn't have to be a guard let, we could just say guard in order, open up the parentheses, root dot left, we're just going to say else, open up the brackets, return false. So, excuse me, y'all. If we traverse the left subtree and we see that it's not valid, we could just automatically return false before we traverse the rest of the binary search tree. Then after we do that, now we need to check if the current node's value is greater than or less than the previous node value, right? So we just set this previous variable up here. Now it's time we get to use it, right? So we need to check if the current node's value is greater than the previous node's value, right? So, and if it's not, then the BST property will be violated and we will return false because we'll know that it's not valid. So we'll just say if let prev equals prev, comma, root dot val is less than or equal to prev. Then we could just return false. Because if the root dot val is, remember this returns a boolean, this is going to return true or false. So if this val is greater than the previous value, then we know it's false. Then we know it's true. If this value is less than the previous value, then we know it's false, right? So that's what this is going to do right here. This right here is going to check if the root value is less than the previous value. And if it is, then it's not. Then we're going to return false. Then we could come down here and we could just say, or first we need to update the previous node's value to the current node value. So we just say prev equals root.val, because remember we're traversing through this, so we need to update the values as we go along. Then we could just recursively check the right subtree, and in order to do that, we could just say return in order, open up the parentheses, root.right. So if we make it this far, then we could just return the in order root.right. Boom. Now we just come up here and we could just start our in order traversal in the function that they gave us by saying return in order, open up the parentheses, root. Now that should be all she wrote, y'all. Let's run it. Let's run it. Ooh, it's accepted, so let's submit it. Make sure it stays accepted, y'all. Let's see. Ooh, look at that, y'all. 0 milliseconds beats 100% of users with Swift, y'all. That's what I like to see. I hope y'all learned something today. Get one more look at the code. It's not too much code, y'all. That was a pretty simple solution today. Hope y'all learned something today, and I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.